Right now, underneath the streets of downtown Seattle, there is a fault system that 4 million people live directly on top of, commute across, and build skyscrapers over, without most of them ever thinking about it. Right now, researchers digging through the layers beneath that fault have newly confirmed something that upends a number geologists have relied on for years, a number about how often this ground is actually supposed to break. Right now, that revised number is not measured in centuries you'd casually round up or shrug off as a distant someday concern. It's measured in a time frame roughly 14 times shorter than what the standard picture assumed. And right now, the scientist who led the study is on record saying flatly that this newly confirmed pattern changes how dangerous this fault actually is. Stay with me, because by the end of this, you'll understand why a quiet background hazard most Seattle residents never worry about just got newly confirmed to be a far more active threat than the official risk maps have been showing. This is not a rumor pulled from social media or a viral clip taken out of context. This is a peer-reviewed study published on January 27, 2026, in the Geological Society of America Bulletin, led by research geologist Stephen J. Angster of the United States Geological Survey's Earthquake Science Center, alongside co-authors Brian Sherrod, Jesse Pearl, Lydia Staish, Wes Johns, and Richard Blakely. It has since been covered by Science Daily, Phys.org, SciTech Daily, and Geology Page, all independently reporting the same central finding, pulled from the same paper. When a result comes out of the USGS's own seismology unit, gets published in one of the field's most rigorously reviewed journals, and then gets confirmed independently by multiple science outlets reading the same data, that stops being speculation and becomes the number the rest of the field now has to work from. Before the specific numbers land, it helps to understand what geologists were actually working with before this study changed the picture. Teehee-Seattle Fault Zone is a network of faults running east to west directly beneath downtown Seattle and Elliott Bay, passing under West Seattle, Bremerton, and Bellevue, and sitting less than a mile from the city's downtown core. Geologists have long known the fault's main strand last ruptured roughly 1,100 years ago, around 900 AD, in an earthquake estimated between magnitude 7.0 and 7.5. What they didn't have a confident answer for was how often that main fault, or anything connected to it, was actually likely to break again. The working assumption for years was that a rupture on this scale of fault happens on a TM scale stretching past 5,000 years, treating Seattle's downtown fault more like a slow geological metronome than an active daily concern. That quiet, slow-moving hazard, reputation, is exactly what makes this story worth telling now. For decades, the Seattle Fault Zone sat in public consciousness as the sleepy cousin of the far more famous, far more feared Cascadia Subduction Zone offshore. A fault so slow-moving on paper that most residents never gave it a second thought between news cycles. That reputation held up for years, largely because nobody had gone looking closely enough at the smaller structures riding alongside the main fault to know otherwise. What has now been newly confirmed through direct trenching, radiocarbon dating, and tree ring evidence rather than assumption is that the quiet reputation itself was built on incomplete data, and the actual rupture history hiding in the rock beneath Seattle tells a considerably more active story. The Seattle Fault Zone is also not the only source of shaking this region already takes seriously, which is part of why it was already a monitored, high-priority hazard well before this study. Seattle's earthquake risk breaks down into 3 distinct categories that emergency planners track separately. Crustal, or shallow, earthquakes occur near the surface along faults like the Seattle Fault Zone itself, producing intense, localized shaking. Deep intraplate earthquakes strike within the Juan de Fuca plate as it dives beneath the continent, the category responsible for the magnitude 6.8 Nisqually earthquake in 2001, which caused roughly $2 billion in damage and around 400 injuries, and the magnitude 6.8 Olympia earthquake in 1949, which killed 8 people. And then there's the offshore Cascadia megathrust, capable of the kind of magnitude 9.0 rupture the region experienced in 1700. 3 separate mechanisms, 3 separate hazard profiles, all converging on the same metropolitan area, which is exactly why Washington State already runs a dedicated seismic hazard program and why any newly confirmed change to one part of that picture, like the recurrence interval in the Seattle Fault's secondary structures, matters enough to make researchers put out a public statement about it. That is the number this new research just overturned, and the mechanism behind it is worth explaining clearly, because it's the entire reason that didn't expect framing in this story is earned rather than exaggerated. Angster's team wasn't studying the massive main fault everyone already worried about. They were investigating 2 previously undocumented secondary faults sitting inside the same broader fault system, structures they named the Lytle Beach Fault and the Vasa Park Fault, both tucked into the folded rock directly above the primary, buried Blakely Harbor Fault. To find them, the team used magnetic surveys to detect subtle variations in the bedrock, LiDAR imaging that strips away Seattle's thick tree canopy digitally to reveal ground scarps invisible from the surface, and then physically dug trenches across those scarps, dating the layers inside using radiocarbon analysis and the growth rings of trees that had been killed by past ground ruptures. What that combination of methods revealed is that these secondary faults have been rupturing on their own, independently of the massive main fault, roughly every 350 years over the past 2,500 years. Stack that recurrence interval against the more than 5,000-year figure long assigned to the main fault. And the difference comes out to roughly 14 times more frequent. The equivalent of discovering that a warning siren you assumed only went off once in a great while has actually been going off multiple times within a single lifetime, just quietly enough that nobody had connected the pattern until now. Angster put it plainly in comments about the findings, explaining that the surface ruptures recorded across the Seattle fault zone over the last 2,500 years have actually been dominated by these smaller, previously overlooked secondary earthquakes, not by the giant, headline-grabbing main fault rupture everyone assumed was the primary threat. The most recent of these secondary ruptures, based on the tree ring and radiocarbon evidence, likely struck sometime in the early 19th century, meaning the mechanism producing repeated, city-shaking earthquakes beneath downtown Seattle has been active far more recently and far more often than the standard hazard picture ever accounted for, right up until this study finally traced it back through the rock layers themselves. Let's rehook here for a second, because this finding doesn't exist in isolation. From everything else geologists already knew was sitting beneath this city. The Seattle fault zone is only one piece of a much larger seismic puzzle in the Pacific Northwest. Offshore, the Cascadia Subduction Zone, where the Juan de Fuca Plate dives beneath North America, produced a full margin. Rupture in the year 1700 estimated at magnitude 9.0, and the U.S. Geological Survey currently places the odds of a comparable Cascadia rupture within the next 50 years at somewhere between 10 and 15%. Layered on top of that, the USGS's National Seismic Hazard Model puts the odds of a magnitude 6.7 or greater earthquake within 60 miles of Seattle at roughly 65% over the next 30 years, and a 25% chance of a magnitude 7.0 or larger event in that same window, with the Seattle fault zone itself capable of producing a maximum credible magnitude of 7.5. This region was never actually a quiet one on paper. What Angster's team newly confirmed is that the specific mechanism inside downtown Seattle's own backyard fault has been firing on a much shorter clock than anyone had verified, sitting right underneath the exact spot where 4 million people live, work, and build. That distinction matters because of what a Seattle fault rupture would actually do to the city sitting directly above it, which is different in character from what an offshore Cascadia event would do. Angster himself has drawn that contrast, noting that a Cascadia rupture would bring long, powerful shaking to Seattle from far offshore, but that a rupture on the city's own local fault system, precisely because it sits so close, carries the potential to be significantly more destructive to Seattle specifically. Much of the city's waterfront, industrial district, and parts of downtown, including Pioneer Square, the Soto neighborhood, and the Duwamish River Valley, were built on filled land over former tidelands, ground that is especially vulnerable to liquefaction, the process where saturated soil essentially loses its structural strength during intense shaking. A Seattle fault earthquake could also generate a local tsunami reaching up to 16 feet, striking the shoreline within seconds of the shaking, starting and flooding low-lying areas within about 5 minutes, far too fast for any offshore warning system to help. None of this rests on a single team's word alone. The Washington Geological Survey has independently documented the Seattle fault's historical rupture around 900 AD and its likely connection to the nearby Saddle Mountain fault system, while the broader USGS National Seismic Hazard Model, built from decades of separate research across the Pacific Northwest, already had this fault zone flagged as a serious risk before Angster's team ever started digging trenches near Little Beach in Vasa Park. Researchers also note that the Seattle fault zone helps absorb ongoing tectonic strain building up between Portland, Oregon, and Vancouver, British Columbia, and is estimated to account for roughly 15% of the total strain released across the entire Pacific Northwest, a substantial share for a single urban fault system to carry. What the new study adds is not a brand new hazard nobody had heard of. It's a newly confirmed, much shorter recurrence interval sitting underneath a fault system regional agencies were already treating seriously, which is exactly why multiple independent science outlets picked the story up the moment it published, and why it's worth understanding clearly now, rather than filing away as background noise. Now, for the part that has to be said, honestly, because even a newly confirmed finding like this one comes with real limits on what it can and can't tell you. This study identifies a shorter average recurrence interval for secondary fault ruptures across a 2,500-year window. It does not predict exactly when the next rupture on these specific faults will occur, and researchers are explicit that estimating recurrence intervals from limited paleoseismic evidence carries genuine statistical uncertainty, especially over such long timescales. The main Seattle fault itself is currently sitting at roughly 1,100 years since its last major rupture, against an estimated average recurrence somewhere in the thousands of years, which places it somewhere in the middle of its own cycle without telling anyone a specific countdown. What has genuinely changed is scientists' confirmed understanding of how this fault zone behaves, not a prediction that a specific earthquake is now imminent. Treating a newly confirmed recurrence pattern as a countdown clock would be the kind of overreach that misrepresents careful. Paleoseismic science and researchers studying this fault have been careful not to make that leap themselves. It's also worth being clear that this confirmation is a scientific finding, not a live event. Nothing shook beneath Seattle to produce this story. What changed is the confidence behind a number, refined through years of fieldwork that finally reached publication, not a sudden crack opening in the ground this week. Given all of that, there's a real practical layer worth taking from this, straight from the agencies that track it. Washington State's Shake Alert system can provide anywhere from 10 to 90 seconds of warning ahead of shaking from a distant rupture, enough time to drop, cover, and hold on before the worst of it arrives. Emergency planners recommend maintaining at least a 72-hour emergency kit, with 2 weeks of supplies being the more realistic. Target: given how badly a major Cascadia or Seattle fault event could disrupt regional infrastructure like bridges, ports, the electrical grid, and water systems. Securing heavy furniture, confirming your specific neighborhood's liquefaction risk, particularly in filled areas like Pioneer Square, Sodo, and the Duwamish Valley, and having a family communication plan are the same basics regional emergency. Management offices have been repeating for years, and currently only an estimated 15 to 20% of Seattle area homeowners carry earthquake insurance, a gap worth closing well before any fault beneath the city decides to test it. Hundreds of older unreinforced masonry buildings across the region also remain occupied, while retrofit programs meant to strengthen them stay incomplete, which is exactly the kind of gap a newly confirmed, more active fault system makes worth closing sooner rather than later. There is something worth sitting with in the idea that the ground beneath one of America's largest cities has been quietly rupturing far more often than the official record showed, not because the earthquakes themselves were new, but because nobody had traced the pattern in the rock closely enough to see it until magnetic surveys, LiDAR, and a few carefully placed trenches near two barely known faults finally pieced it together. The main fault beneath downtown Seattle is still sitting exactly where it's always been, still following whatever timeline it's been on for thousands of years. What changed is that scientists can no longer treat this fault zone as the slow, once-in-5 millennia hazard it was assumed to be, because the smaller faults riding along beside it have been doing their own quiet, far more frequent work the entire time. Tell me in the comments which part of this actually surprised you more, learning that this fault system has been rupturing roughly every 350 years instead of every 5,000, or realizing that Discovery was sitting 60 feet under a quiet Seattle area park the whole time, waiting for someone to finally dig there and look.